Hello, this is Guanting Liu, and my supervisor is Levy. My talk is about strong approximations for stochastic processes driven by Levy processes. This is the structure of my talk, and my research project actually starts later in section 3 of the talk. That's about a positivity preserving numerical scheme for something called the alpha CV process. But before that, I'll use some pages to define what it's a strong approximation and what are the Levy processes we consider for the jump in our stochastic process. So first of all, let's consider a very general expression, an integral expression for a stochastic process. Uh, a stochastic differential equation expression for the stochastic process X. Yeah, I use function b for the drift and function sigma for the diffusion. I only assume they are just some measurable functions here. And w, it's the one-dimensional Brownian motion, the only stochastic driving force, underlying driving force in this stochastic process. And if we are given such a stochastic differential equation, how do we simulate it numerically? Suppose we only have the ability to generate normal random variables. That comes to the idea of approximating stochastic differential equations. A very classic method of doing that, it's the Euler-Maruyama numerical scheme. For that, let's consider a uniform n-interval time grid for the fixed time length t, from 0 to t over n, 2t over n, 3t over n, all the way to t. And on that grid, the Euler-Maruyama approximation for the process X is given by the following recursion. A very intuitive expression for time integral, for time integral we have the time increment, the summation, and for diffusion integral we have the Brownian increment and summation. Moreover, each of these Brownian increments, delta W T0, T1, T2, it's just a normal random variable, independent from the rest. So this is a classic, convenient, and also strongly convergent approximation for a stochastic differential equation. This is a standard result, and you can find it in many textbooks. Suppose the drift coefficient b and diffusion coefficient sigma, suppose they are Lipschitz continuous, then the Euler-Maruyama scheme, it's a strong approximation with convergence rate a half. And the mathematical meaning of that is as the following. The strong error expectation of the difference, it's less than or equal to number of time intervals to the power minus a half. And we call this power a half here, the strong convergence rate. C, it's some positive irrelevant constant depending on other parameters. And besides this basic case, the Lipschitz continuous case, there are also other results for less regular coefficients. For example, for Holder continuous drift and or diffusion, and maybe for diffusion or coefficient, diffusion or drift with discontinuities, there are other results available. So that was about strong approximation and a very classic method being the Euler-Maruyama method. Moving on, for jump extension in a stochastic differential equation, we use the notation of a Levy integral here. Let's look at this as a very similar form with an extra Levy integral at the end. And for the new driving force here, the dynamic Z, we consider a pure jump Levy process characterized by the Levy measure nu. And the easiest example for this jump is a Poisson process, which we can get by taking the Levy measure nu to be a direct measure at 1 multiplied by the intensity lambda. That gives us a Poisson jump with intensity lambda. So with this notation, this say class of Levy processes instead of maybe just a Poisson process, we're able to create many different types of complicated, difficult jumps. The Poisson process, compound Poisson process, or alpha stable process, and all other Levy process with finite or infinite variation, finite or infinite activity. Here, let me spend more time to talk about the idea of infinite activity. Just recall undergraduate level of probability theory, or maybe actuarial science. When we talk about Poisson processes, we always associate it with waiting times between each jump. That image gives us an impression of sparse jumps of the Poisson process, which isn't the case for example, the alpha stable process. For an alpha stable Levy process, the only thing we can do is for a fixed time interval, discuss the distribution of the counts of the alpha stable process. Because there is always a, say, non-infinitesimal probability of having an infinite number of jumps within no matter how small a time interval. So it is impossible for us to talk about waiting times between each jump of an alpha stable process. And that it's the major difference, or say the major difficulty of an infinite activity process from the standard Poisson process. Okay, so when we use such Levy process as a jump extension in a stochastic differential equation, the immediate thing we need to do after adding the jump is to check existence and uniqueness of solution. Because adding something to your SDE doesn't guarantee you a stochastic process. You need to have unique strong solution. That gives you equivalence between an SDE and a stochastic process. In full language, that it's we need existence of a strong solution, and we also need pathwise uniqueness of that solution. Here are some papers on relevant subjects. Some are about strong solutions of different types of SDEs. They focus on uniqueness and existence only. And the others are from applications, or for example, like our work for numerical approximation. They consider difficult processes, and before moving on to their own topic, they need to check, say, the well-postedness of their new process, that its existence and uniqueness. Okay, so much so that were about the idea of strong approximation and the Levy notation we use for jump extension. I think we are ready to look at my research, what we do is to consider an alpha stable jump extended version of the CV process, the constant elasticity of variance process. And following convention, we name it the alpha CV process. For this alpha CV process, we designed a numerical approximation scheme which also preserves positivity, and at the end we proved strong convergence of the scheme. First, about the stochastic process. Before the jump extended version, let's look at the traditional diffusion version. So with this stochastic differential equation with a mean reverting drift and a diffusion coefficient to the power q with q from half to 1, if we take q equal to a half here, we have the Cox-Ingersoll-Ross process, the CIR process. If we take q from half to 1, we have the CV process. CIR and CV, these are very popular models in financial mathematics, for example, for modeling interest rate or for stochastic volatility. And they are positive for most of the cases. Then alpha CR and alpha CV. Similarly, we just simply add on the jump extension at the end of the SDE. And for the jump dynamic here, we very specifically consider a compensated spectrally positive alpha stable process, which is independent from the diffusion W. Luckily, we have existence and uniqueness for solution of this SDE right away. We'll talk about that reference later. A bit more about the jump here. The compensated spectrally positive alpha stable jump. This Levy process can be uniquely represented by the following Levy triple. First of all, we have a very specific exact form for the Levy measure nu here. Power -1 minus half, support from 0 to infinity with alpha in 1 to 2, and the convergence matrix A it's 0, meaning that we only consider pure jump process. The drift, it's a compensating drift, meaning the whole process that it's a martingale. Just briefly on the origin of such a bizarre process. Such processes were originally studied under the context of continuous time limits of branching processes with immigrations. In Jaume Scotti, they introduced one of such processes, the one being CIR extended with alpha stable jumps. They introduced it into financial mathematics to model sovereign interest rates, and they named it the alpha CIR process. And that's where the convention comes from. Later on, for this specific alpha CIR process, Lee and Taguchi designed a positivity-preserving, strong approximation scheme and proved strong convergence for the scheme. For these alpha CIR and CV process, about existence and uniqueness, we have two papers from the same team of researchers. They provide existence and pathwise uniqueness of positive strong solutions to the alpha CIR and alpha CV process. Good, we're lucky. Available result. Though the keywords here I want to point out is positive strong solutions, meaning that adding on the alpha stable jumps, these are still positive processes. And I think that's That might be a reason why Jalma and Scotty introduced such process to model sovereign interest rate. For this alpha CI and alpha CV processes, how do we simulate them? How do we approximate them? The Euler-Maruyama scheme? It does work for alpha stable extended CRI and CV, and it's proven in this paper. And it is still a very intuitive and convenient, strongly convergent approximation, but it loses an important feature of the original stochastic processes, that its positivity. The reason for that it's simple, because thinking of the expression of EM scheme or the Maruyama scheme, the increments delta W and delta Z, if you have the jump, they are just normal and stable variables, and they of course can have negative values. So although the original jump stochastic processes are positive, and although the Euler-Maruyama scheme is strongly convergent, the fact that the scheme can give out negative steps from time to time, it's at the very least an inconvenience. So at this exact point comes the demand for positivity preserving numerical schemes. And that is the focus of our study. We want to create a positivity preserving strong approximation scheme for the alpha CV process. And boom, that's it. This is the high point of our research. What we have here, this scheme starting from x0, represented by the recursion. See from ti to ti plus 1. This is just some substitution. This is a positivity preserving scheme for the alpha CV process. And we also prove strong convergence for the scheme. When Q is between half and 1, we have the following strong error, with the convergence rate being 2 minus alpha over 2 times 3 minus alpha. And that's about all of our recent research. A bit more story on the research. We've been on this project for more than 1.5 years, and after the last conference, the last postgraduate conference, a remarkable achievement of our study is that we obtained bounded alpha moments of the numerical scheme. Being more specific, we have such moments, such beta moments, being finite for beta strictly less than alpha. And that's something we dreamed of last year and obtained only very recently. Having these bounded moments allow us to lift the boundedness requirement on the jump coefficient, and hence to avoid many detours in the method of proof. This is a huge improvement compared to previous work such as the work on alpha CIR by Lee and Taguchi. And even recently, we're still trying to improve the convergence rate. Just take this for example, the current convergence rate 2 minus alpha over 2 times 3 minus alpha for the CV, that it's when Q it's between half and 1. It doesn't depend on the parameter Q anymore. Moreover, along the way of improving the convergence rate, one of the techniques we use also helped us to improve the convergence rate in the alpha CIR case, to improve its strong convergence rate from a logarithmic rate, as in Lee and Taguchi, to a polynomial rate. Now we're still trying to improve convergence rate. Just one story, frequently in their 2020 working paper, they study a mean field extension of the norm Lipschitz Levy-driven SDE from Lee and Minnick, and they prove a convergence rate for the corresponding Euler-Maruyama scheme. Their problem kind of contain our problem, but the scheme to consider it's a different one, just the standard Euler-Maruyama scheme. Although not absolutely comparable, their convergence rate is still faster by a factor of 2 over alpha than ours, and that gives us a motivation to keep improving our convergence rate. That's about all of my last project on a positivity preserving numerical scheme for the alpha CV process. And later on in the same area, we might consider other strong positive preserving approximations for the alpha CR and alpha CV processes. Or we might study different Levy-driven processes and maybe study strong approximations for them. One of the process that we are interested, it's the Al-Sahalia process. The SDE here, it's already the jump extended version. But just look at the drift and diffusion here. We can see that it's a very different stochastic process. In the drift, we have an inverse term, and R being greater than 1, a superlinear term. And in the diffusion, we have a superlinear term, rho greater than 1. And for the sake of simplicity, we only maybe starting from an alpha stable jump here for the time being. And we don't have existence in uniqueness for it yet at the very beginning. And without that, we don't even know whether we have such a process, such an alpha Al-Sahalia process. There are relevant studies. There are studies on Poisson extended Al-Sahalia process with existence and uniqueness of solution and strong convergence of the corresponding Euler-Maruyama scheme. And there are also studies on solutions for Levy-driven SDEs with superlinear, but only diffusion, not drift. They are considering sublinear drift. So we don't have any result handily available, and we are quite interested to proceed. That's all of my talk today. Thank you. Some references. Try to pause a few seconds on each page in case anyone are interested. Page 2. Page 3. 4. 5. 6. Lee and Taguchi. 7. Okay, that's all of my talk. Thank you. Thank you for listening.